Right, okay, so let me try to explain with our vector equations and the genesis of it. How they've been actually, the theory behind it, and what's all about. Okay, so vector equations are nothing but just a very simple way of representing a straight line. Actually, it's probably one of the very simplest way of representing a straight line, vector equations. So let's say, take some pens. So let's assume we got a straight line. We have a straight line given by this. This is a straight line. This is a straight line here. And normally a straight line can be depicted by a few types of equations. We can use Cartesian equations. Cartesian equations to depict it. Cartesian, isn't it? Cartesian ones are basically based on y equals mx plus c. That's one way of depicting it. What we're saying depicting means when you know the x coordinates, you would know the y coordinates. Or if you know the y coordinate, you would know the x coordinate. So that's the one way of finding a relationship of these points. You know, it's all about finding a relationship of these points. There are infinite number of points. As long as you know the x coordinate, you would know the y coordinate, vice versa. In a similar manner, you can also use parametric equations, you know, using t's and all that. So there are a few ways parametric equations, parametric, isn't it? For example, parametric equations can be written like x equals 2t plus 1, y equals t. The y equals t, that's a parametric way of explaining a straight line. So for different values of t, we got different values of x and y. See? In a similar fashion, we can also use vectors to depict or describe a better word, describe straight lines. Okay? So that's what our topic here. So that's what we are focusing on, how to explain, how to describe straight lines using a vector equation, using vectors. So however the goal or the motive is the same, to find these points, that's our motive. So let's see how it's done, okay? Right, so let me get it off this. Alright, so let's say we got a straight line again, straight line like this, and we try to find a vector equation. That's basically based on C4. I'd like to mention that, vector equations. To do that, like I said before, the whole idea is to find the points. Okay. Now, if you look into, let's say this line is actually on a grid, in an xy plane, on xy plane, xy plane like that. So let's say now these points we know we can be represented them as position vectors, isn't it? We know, if we know the positions, then we can say, see, that's position vector R1, isn't it? You see, it could be 2i plus 3j or whatever, and this could be another R2. You see, it can be 7i plus 4j, whatever. It doesn't really matter. You know, see, any point. Sorry, they must be straight lines. Okay, these are position vectors. See, like that. We can depict many position vectors, as many as you want, like that. Plenty, like that. So if we can find an equation for this general formula for R, then we can work out these points basically. That's the whole idea. See, that's the whole idea. Okay, so let's see how it's done. Now let's assume we know one point, a fixed point, a fixed position on this line. A fixed point. For example, let's say that point is known. A fixed point. As a fixed vector, as a fixed point. Fixed point. It's given as, let's say that's given as f, if you will, because it's fixed. Fixed means it's not really fixed. Obviously, all these points are fixed anyway. The reason I said fixed means it's a known point. It's known. It could be 2i plus 3j or whatever. All right, for an example, or let me write an example as well for clarity. That can be written as example 2i plus 4j. Okay. Now, on the other hand, let's say we know a vector along this line. We know some vector along this line. It could be along this line or parallel to this line. It doesn't really matter. Because why? Vectors can be translated up and down. It doesn't really matter. We can't rotate them, that's true, but we can translate them. We can just move them like that. It's fine. As long as the angle retained. Okay? Like that. So let's say we know a vector, either it is on this line or just parallel to it. Let's say we know a vector on this line which is parallel to that given as A. That P is given as A. Okay? Now then, so we can translate this vector like that if you want. If I want, I can overlap with the line easily, right? Isn't it? So using that, I can depict any point on this line like this. For example, I can depict any point. Let's say this point I want to depict. That point. So that's normally, that is the R, isn't it? I'm trying to depict that one, that point. To depict this point, I can write F plus lambda A, because that's A. This could be because that is a small piece of it. I don't know how the length of that. So I can write generally, it says lambda or mu or gamma or T, whatever you like. So I can write this as lambda A. Okay, that vector is lambda A vector. Because that piece is lambda A, then it should be lambda A. Lambda is a scalar. So that depends on the length from there to there, depends on the distance from there to there. So I can write lambda A. Now can you see here, now what we have created is actually nothing but a triangle. See? So there's a triangle we have created here. You see, there's a triangle. Can you see a triangle here? So if you got a triangle, now we can write the triangle equation. That plus that equal to R. Simple as that. There you go. So F equals, sorry, not F, I mean R equals, R is any general vector on that point. Okay, Paschen vector in general Paschen vector equals to F plus lambda A. That's it. That's the genesis of vector equation. As simple as that. So if you want, we can sub these values. For an example, F can be 2i plus 4j. So I can write this one like this. F is 2i plus 4j plus lambda times. Let's assume A is given as that vector that given as, let's assume minus 2i plus j or whatever. Just taken just something randomly, so I can just put it there. Basically minus 2i plus j. That's equals to R. That's a vector equation. That's it. So for different values of lambda, I get different points. For example, when lambda is 0, the whole thing becomes 0. So I recover 2i plus 4j, that point. See, when lambda is 0, I get a fixed point. This makes sense. When lambda is 1, I get a different point. When lambda is 1, I'm going to get basically 5j. You know, I'm going to get 5j because that cancels out when lambda is 1. You know, it's become somewhere there, 5j. It could be that even. Lambda is minus 1, for an example, I'm going to get another point. For different values of what I'm saying here, basically, different values of lambda yields different points of different R values, which means different points on this line. Because every time what we are doing for each lambda, we're creating a little triangle. You know, different triangle, but the triangle is located on this line. See? So that's what exactly happened. Alright, I think is it clear? I think it is clear. And also we can write this equation using matrix form. We can write this one like this. We can write 2 minus 2 lambda. See? 2 minus 2 lambda. 4 plus lambda j. 4 plus lambda. That's it. If you want, you can write it like this. That's I, whole I, you can take together. 2 minus 2 lambda, 4 plus lambda. Alright, if you want, you can repeat it like that. Now, let's say this is obviously this is a straight line anyway. If it's a straight line, then we should be able to find, for an example, we should be able to find x and y intercepts. Okay, so let's see whether we can work out x and y intercepts. And we know when for an example, when the x-intercepts what really happened, the y coordinate is 0, isn't it? Because it's intercepting. See, that line is going to go like that if I do a small construction, it goes like that. But it's intercepting here at that point, the y coordinate is 0. The y coordinate is 0. Then I can write, because y coordinate is 0, I can write 0, because that's the x, y, isn't it? But I don't know the x coordinate, so I can write that is probably t, which means ti plus 0j, okay, which is basically equals to ti plus 0j. So I depict it again in the matrix format, or the column vector format, or whatever. So if you can find t, then we can know the intercept. So what we can do then, I'm going to equate that to that. Basically simple as that. Because why? That's a value for r, isn't it? So the r must be equal to that at this point. Okay? Because r goes everywhere like that, like that, like that, can just that. So then I'm going to write 2 minus 2 lambda, 4 plus lambda equals to t0. So in this one, I'm going to get lambda equals, because 4 plus lambda equals 0, which means lambda equals minus 4. Subbing into that, lambda equals minus 4, I'm going to get t equals 10. Because minus 8 plus 2, 10. So which means that's 10i. 10i is the place they intercept. Okay? So we can say that place intercepting 10i. Obviously, this is not a right proper drawing. It's not a proper calibrated drawing. If you do properly, then you will really get it 10i somewhere here. But that's for the time being. That's the answer. That's the answer anyway for this in this question. So that's how it is. Okay. So that's the x-intercept 10i. Or in coordinates, or in what you call in Cartesian coordinates, you can write as 10, 0. Okay. Now we can work out similar fashion. Very similar fashion. We can work out the y-intercept if you want. And y-intercepts. What happened? That's the y-intercept. The I becomes 0, isn't it? There's no I becomes 0. So I can say it's 0, let's say mu, which means 0 I plus mu j. So then again, this and that should be equal, this and this should be again equal, but I'm saying R should be equal to that. So you can equal them. 0 mu equals 0 plus, 0 mu equals to 2 minus 2 lambda, 4 plus lambda. That's it. That gives us lambda equals to 1 in this case, because 2 minus 2 lambda equals 0, lambda equals to 1, subbing 1 there, mu equals 5. So mu equals 5 means they basically cross that with 5j basically. Okay, 5j. Or you can write in terms of Cartesian format 0, 5. Alright, so that's basically the basis of it. I think you understand. If you know the vector equation, we can do many things that we can do with Cartesian equations, using vector equations. Also, if you want, we can, if you look into this a bit carefully, we can actually convert this, if you want, really into Cartesian equation as well, because we can use this to find the gradient, and we have fixed point, we can find that, and all sorts of things can be done, you know. Yeah. In a similar fashion, we should be able to convert a Cartesian equation into vector equations as well. Probably I'll discuss in another time that. Okay. All right then. I think that's good enough.